Hello and welcome to the last part in this series. We start with problem number 96. The magnetic field inside a long solid cylinder is given as this, where the values of alpha and A are also given. What is the current in the conductor? We use the Ampere's law, that is the line integral of H is equal to I, and we'll take a path that is circle along the direction phi with a radius A. So this integral is essentially evaluated to h at r equal to a times 2 pi a, and that would be our current. When r equal to a, alpha r is equal to pi. So we calculate h at r equal to a, and since alpha r is equal to pi, the first term goes to 0 and cos of alpha r gives -1. This minus 1 multiplies to 1, so we have h is equal to 10 to the power 2 divided by a times a divided by alpha, which is given by pi over a. And to calculate the current, we have to multiply it by 2 pi a. So let's simplify things. A cancels out, pi also cancels out. We have 200 s squared, and putting the value of a to be 1 by 5, we have 200 by 25, and that is 8. So option C is the correct answer. Problem 97. A steady current I flows through the loop as shown in the figure. The magnitude of the magnetic field induction at point O is. So O is supposed to be the center of the two concentric circles, half circles. So we know the magnetic field produced by a circular loop carrying current I with radius a is given by mu naught I divided by 2a. So if the circle is cut into half, so we have only half circle, the magnetic field contribution would be exactly half of that. So that is mu naught I divided by 4a. In this case, we have two such half circles. The current is going in opposite direction. So for this inner half circle, we will have mu naught I divided by 4a, and for the bigger half circle, we will have mu naught I divided by 8a, and the minus sign is due to the fact that the current is going in the opposite direction, so magnetic field will be directed in the opposite direction, and that is equal to mu naught I divided by 8a. So option D is the correct answer. Problem 98. A metallic ring of area 1 centimeter squared and resistance 10 ohm is placed in a time-varying magnetic field given by this, where B is measured in Tesla and T is in seconds. The net charge that flows past any point in the ring from t equal to 0 to t equal to infinity is. So we know the induced EMF is given by the rate of change of magnetic flux, and that is dB by dt times the area. So E we can write as current times the resistance, and which we can also write the change of charge times the resistance. So we have dq by dt is equal to A by R dB by dt, or the change of net charge is given by A by R integral of dB from 0 to infinity, that is A by R times the change of value of the magnetic field at infinity minus 0. So let's calculate these two things. So when t is equal to infinity, the exponential term will dominate, and b at t equal to infinity would be 0, but b of t at 0 is given by 2. So we have 2a by r, that's the net change in current, and this is 2 times 10 to the power minus 4 divided by 10, and that is 20 microcoulomb. So option D is the correct answer. Problem 99. The input given to an ideal op-amp integrated circuit is this. So the correct output of the integrated circuit would be. So note that the input current input voltage is 0 from 0 to T naught. So we should expect the output voltage to be 0 from 0 to T naught. So this eliminates option B and option C. And since this is an integrated circuit, so we'll have integration of B of I dt, and assume this is C, so this would be C dt, and with the integral would look like Ct. So the output voltage will linearly increase from T naught. So option A would be the correct answer. Problem 100. In an impure copper, the collision time for phonon scattering and impurity scattering are respectively this and this. If for pure copper the effective collision time is this, then the ratio in conductivities of pure to the impure copper is. Recall from Drude model, the current density J is given by N E squared tau divided by M times E. This tau is the collision time. So, and this is essentially the conductivity. So sigma conductivity is proportional to the tau, the collision time. If you have impurities, then the total collision time 1 by tau is given by 1 by tau due to the phonons plus 1 by tau due to the impurities. Or tau is given by T phonon times T tau impurities divided by tau phonon tau impurities, and that is given by 2 times 4 times 10 to the power minus 20 divided by 6 times 10 to the power minus 10, and tau is now is equal to 4 by 3 times 10 to the power minus 2 minus 10. So sigma pure divided by sigma impure is tau pure divided by tau impure, and this is equal to 2 times 10 to the power minus 9 divided by 4 by 3 times 10 to the power minus 10, and this is equal to 20 times 3 divided by 4, and that is 15. So option B is the correct answer.